All right, Gibson here. Today we're going to look at our first lesson in this new unit on circular motion. So let's look at our objectives. First one is we're going to make a distinction between rotation and revolution, two different ways to describe circular motion. We're also going to look at two different ways to describe the velocity or the rate at which an object rotates. Either it's linear, or sometimes we call it tangential velocity, and angular velocity. We'll explain why when an object is moving in a circle at a constant speed, it's still undergoing acceleration. And we call that acceleration centripetal acceleration. And it turns out it depends on the object's speed and the radius of the circle that it's traveling in. And then the last objective is what is the force that causes centripetal acceleration? All right, so this first concept, we're going to look at the example of the spinning wheel. How is the circular motion different between the wheel itself and the reflector on the spokes? Well, the wheel we would describe as rotating, or it rotates or spins around its center axle. The reflector, we're going to use the word revolves. It revolves around the center axle. But here's the key distinction, right? The wheel is turning about its own internal axis. The point where it rotates, the center axle, is in the center of the wheel itself. That's different than the reflector. The reflector turns about an external axis, right? The axis of the wheel that it's rotating, or I'm sorry, revolving around is not on the reflector itself. Okay, so we basically, all circular motion will occur in one of these two cases. So here's the official definition. A rotation is when an object turns or rotates about an internal axis, like the bicycle wheel. And the revolution is when an object turns or revolves about an external axis, like the reflector on the wheel. So let's look at a couple more examples. If we throw a football and do it properly, right, we have the football spinning, or we say we throw it in a nice perfect spiral. So would that be a rotation or revolution? Well, it's going to spin around its own internal axis, around the two kind of pointed ends of the football. So we would describe that as rotation. How about an orbiting satellite? Well, it revolves around the Earth, right? The center of the Earth, but it's not, the center of the Earth is not part of the satellite itself. So we would say that it revolves and its axis is external. All right, let's look at another example. How about the Earth? Does the Earth rotate or revolve? Well, let's first ask, does it rotate? And yes, it does, right? We know it rotates. That's what gives us our night and day. What is the axis? Well, the axis, right, is internal through the North and South Pole. How often does it rotate? It does it once every 24 hours. So the Earth definitely is rotating. But does it also revolve? Well, what does it revolve around? Remember, it would be around an axis that is external. And of course, we know the Earth also revolves around the sun, right? So the axis is the center of the sun. How often? Well, our Earth year, right, is about 365 days. So it would look something like this, right? The size of the Earth is greatly exaggerated here compared to the sun, but you get the idea. It's doing both, revolving around the sun and rotating around its own internal axis. All right, so key vocabulary terms here, the difference between rotation and revolution. All right, so now let's talk about how we would describe the speed at which the wheel is turning. Okay, so we have 3 points on the wheel, A, B, and C. A is the center on the axle. B is about halfway on the spokes, and C is out on the rubber part of the tire. So which of these 3 points has the greatest speed? Well, we can say that all points are going to rotate the 360 degrees or once around in the same amount of time, because the entire wheel, right, is going to rotate in the same amount of time. But which point travels the farthest with each rotation of the circle? So think about the path that these points are tracing out, A, B, and C, right? Which point is drawing the largest circle, the circle with the largest circumference? And that, of course, would be point C, right? C has to travel farther in the same amount of time as points B and A, therefore it's going to have the greatest speed. Well, what about point A? Point A, we could say, has 0 speed because it's basically just rotating on the axis, but it really doesn't have any circumference, right, that it has to travel as the wheel rotates. So we often call this linear or tangential speed, right? It's the speed of an object moving along the central or circular path. The direction of motion is always tangent to the circle. So sometimes we also call this tangential speed. So the symbol we use is V, just like for velocity from the beginning of the school year. And the subscript T stands for tangential. So if I were to draw the velocity vectors on the wheel, it would look just like the red arrow here, right? It's going to be tangent to the circle. Another way to think about this, what if we were just spinning a rock on a string, right? And if we were to cut the string, what direction would the rock fly off? Well, it wouldn't continue to fall or rotate in a circle. It would fall straight at whatever that direction was the instant that we cut the string. That's what we refer to as the tangential direction and the tangential velocity. The units here are meters per second, just like regular velocity. All right, so let's go through a little activity. What if we wanted to calculate the tangential speed of point C on the wheel? What would we need to know? Well, we need to know how far it travels, and we need to know the amount of time it takes to travel that. So for a spinning wheel, we basically want to understand what would be the total circumference, right, once around the wheel, and how much time does it take to rotate one revolution. So here's some information that will help us calculate that. Let's say the radius is 0.4 meters, and it does one complete revolution in 1.2 seconds. All right, so our first step is we need to calculate the distance, right? The time we're already given, but what is the distance that it travels in one revolution? And here, just think back to some geometry, right? The distance is equal to the circumference. And the circumference, if you remember, is 2 pi r, where r is the radius of the circle, or in this case, the radius of the wheel. So if we simply plug in 0.4 meters for the radius, we get a circumference of 2.51 meters. So in one revolution, the point C is going to travel 2.51 meters. So now we can calculate its velocity, right? Take its total distance or circumference and divide that by the time for one revolution. So 2.51 divided by 1.2 gives us about that answer's not right, 2.09 meters per second. What should that be? Let me fix that, right? We got 2.51 divided by 1.2. Actually, yeah, that's 2.09. How can that be? Okay, no, that's correct. Sorry. I'm doubting my own math here. Okay, so an example to calculate tangential speed. Total distance that it travels in one revolution, and then how much time does it take to travel that one revolution. Okay, so it's distance over time. Same thing we've been doing, just applied to a circular motion. Now there's another way to describe speed, and that's angular or rotational speed. So we already said, right, all points on the circle will rotate 360 degrees in the same amount of time. So A, B, and C are all going to go around the circle, if we use the time from the example before, every 1.2 seconds. Okay. So when we describe angular speed, all we're talking about is the number of revolutions or rotations in a unit per unit of time. Okay, we're not worried about the distance that it travels. We're simply worried about how many revolutions or rotations it does in a instant of time. The symbol we have for angular speed is omega. That's a Greek letter. It looks like a W. And the units could be different depending on how we measure it. One measure is radians per second. Remember, radian is just a measure of angle. There's 2 pi radians, right, in one revolution. Or more commonly in everyday life, we talk about angular speed in terms of revolutions per second, for example. And maybe even more common things like revolutions per minute, RPM, right? If we look at the tachometer on a car, it tells us the revolutions of the engine in revolutions per minute. Okay, so that is angular speed, as we don't have to worry about the distance that it travels. It's simply how long does it take any point on the circle to go through one full rotation. Okay. All right, now let's move on to the central concept here of centripetal acceleration. In order for, or circular motion, in order for circular motion to occur, we must have a centripetal force. And the centripetal force is a center-directed force that causes an object to move in a curved or circular path. So think about this object, right, that's moving on this circle here. The green arrow kind of shows the direction of its motion. And let's even think about having a string attached to that, right? If we just cut the string, it's going to fly off in a direction that is straight and tangential to the circle. But in order to keep it traveling on the circle path, that string has to constantly be pulling in towards the center in order to keep the object or mass on that circular path. So that pulling of the string is an example of the centripetal force that's directed towards the center of the circle or rotation that keeps it traveling in that circular path or motion. So here's a couple key attributes of centripetal force. It's always towards the center of rotation, and it must be applied through some agent. Okay, now this is key. Centripetal force is not a unique force of its own kind. We've studied lots of different forces, right? We've studied gravitational force, we've studied frictional force, normal force, tension force, a push force, a pull force, electric force we will get into a little later this semester. Those are all specific ways in which forces are applied. Centripetal force is not one of those unique forces. Centripetal force will always be applied through one of those forces that I described, right? If you have an object on a string, the centripetal force is going to be a tension force caused by the string pulling that object to the center. Okay, so let's look at some examples, see if we can identify what is actually applying the centripetal force in order to keep it moving in a circle. So here's the example I just mentioned, a plane on a string, right? What direction is the centripetal force? Well, it's always going to be directed to the center of the circle, okay, along the string in this case. What's applying the centripetal force? It's simply the string. So it would be a tension force pulling on the airplane. How about a car making a turn on a road, a sharp turn? Well, the direction, right, is still going to be always to the center, okay? Always to the center, thing to remember for centripetal force. And what is actually applying that force? Well, think about it in a car. If you're making a sharp turn, what actually keeps the car from just skidding out or traveling in a straight direction rather than responding to your turn of the steering wheel? Well, it turns out it's the friction of the tires and the road, right? The tires gripping the road allows it to apply that centripetal force that keeps the car turning in a circular path. Just think about it. If you're driving on ice with no friction, does it do any good to turn the steering wheel? Not really. The car is just going to keep going in the same direction because you have no way of applying a frictional force or centripetal force through that friction. Let's look at one more example. I don't know what you call this. I think one name is zero gravity. Perhaps you've ridden on one of these at the fair here. You can see people there standing right along the wall of this kind of cylinder here that's spinning at an angle. And it starts out spinning horizontal and then it tilts up. And you get a strange sensation, right, as it's spinning. Feels like you're being pushed back against the wall, right, if you've been in one of these. So the direction is a centripetal force for you is still have to be towards the center, right, to keep you traveling in that circle. And what is applying the centripetal force to the, it should be person, not car. It's the wall pushing against you. Now, to you, it feels like your back is being pushed into the wall, but it's actually the wall pushing into you that keeps you moving in that circular path, right? If you didn't have that wall to push you there, you would just go flying off straight at a tangential line to this circular structure. So for every centripetal force, there is a unique type of force that's applying that, right, in every situation. All right, now how do we actually calculate centripetal force? Here's the equation for it. It's the mass of the object that's traveling in a circle times the tangential velocity squared. Okay, so that's the first type of velocity we talked about, right? Meters per second. How fast is it traveling around the circumference of the circle? And then you divide that by the radius. The units for centripetal force are the same that we've done before, newtons. Okay, so let's look at a simple example here. We have a plane with a mass of 2 kilograms. Its velocity is 6 meters per second, and its radius is 3 meters. So we just plug those into our formula, right? Mass of 2. We take the velocity and square it, 6 squared. Don't forget to do that, and then divide everything by 3. So if we do the math, 2 times 6 squared is 72. 72 divided by 3 is 24 newtons. So we would feel a tug on the string of 24 newtons, but we're actually pulling on the airplane with a force of 24 newtons in order to keep it traveling in a circular motion. Now here's just an interesting question, right? How would the centripetal force of 24 newtons compare with the gravitational force on the plane? Well, the plane has a mass of 2 kilograms, so if we multiply that by 10, we would have a gravitational force of 20 newtons. So this centripetal force, if you were a little bug on the airplane, you would be feeling a force greater than 1g, right? And the faster we spin it, the higher the g force you would begin to feel as the centripetal force becomes greater and greater. All right, the last concept here is centripetal acceleration, because we know that anytime we apply a force to an object, an unbalanced force, we're going to get acceleration. So centripetal acceleration is the center-seeking acceleration of an object moving in a circle at a constant speed. Okay, so it's going to be in the same direction as force, right? Acceleration and force are always in the same direction. Now, Newton's law tells us, second law, that force is equal to mass times acceleration. So if we just divide out the mass from the formula I gave you a minute ago for centripetal force, what are we left with? We're left with velocity squared divided by the radius. That's the tangential velocity squared divided by the radius. Okay, so even simpler to calculate. So if we know the we know the radius and we know the velocity, we can calculate the acceleration. Notice it does not depend on the mass of the object. So does acceleration, centripetal acceleration, change the speed or the direction of the rotating object? Well, notice the acceleration is at a right angle to the velocity. So it's not going to change the magnitude of the velocity or the speed, but it will change its direction. So let's play around with the formula a little bit. How would the acceleration change if the velocity doubles? Okay, so look at the formula up there, v squared divided by r. So if we double the velocity, but we square it, that would cause the acceleration to quadruple. How does it change if we double the radius? So we're dividing by the radius. So if we double the radius, that means we're going to divide by 2. The acceleration will be half as large as the original radius. Okay, one final example here. Let's calculate both the centripetal acceleration and the centripetal force acting on the airplane. Now, we're already given the velocity here, right? 6 meters per second. But I might give you a problem where you'd have to first calculate that, right? What is the circumference? How much time does it take to travel around? All right, let's calculate the acceleration first. So the velocity squared divided by the radius. So that's simply going to be 6 squared divided by 4. So 36 divided by 4 gives us 9. Notice the units for acceleration are the same, meters per second squared, even if it's centripetal acceleration. All right, how about the centripetal force? Well, we could plug it into the original formula, but since we already have the acceleration, we just need to multiply it by the mass. So we're going to take our 3 kilogram mass and multiply by the 9 meter per second squared acceleration we got in the first step, and we get a centripetal force of 27 newtons. All right, that's it. So we know the difference between rotation and revolution. We're able to contrast what we mean by tangential or linear velocity versus angular velocity. We can explain why an object moving in a circle at a constant speed is accelerating, because what is changing is the direction, right? Not the speed, but the direction. And we can describe how centripetal acceleration depends upon the object's speed and the radius of the circle. That's the equation, v squared over r. And we're able to identify the force that causes centripetal acceleration. Like I said, centripetal force is not a unique force itself. It's always going to be caused by the list of different forces that we've been working with, like gravity or tension or friction. All right, that's it. Take a look at the assignment in Google Classroom that goes with this.